Alright, so I'm here to do chapter 29, problem 80. And the question asks, an electric dipole has a dipole moment P, where R is much greater than S, where S is the separation between the charges, as seen in my drawing. And the problem is asking to show the electric potential can be written as 1 over 4 pi epsilon naught times P, the dipole moment, cosine theta over R squared. So over here I have a drawing, and it's the representation of what this problem is asking. So we have just any arbitrary point, x, y, and we're measuring the electric potential at that point based in terms of polar coordinates with r and theta. So what we're going to do first is define V, which equals kq over r. So we have r1 and r3 that are both acting on this point. So it's going to be kq over r1 minus kq over r2, because, this should be r2. Because it's the negative charge, it's actually going to be subtracting, although it's not a vector. So to further define, r1 is equal to the root of x squared plus y minus s over 2 squared, as you can see by the geometry. And then r2 equals root x squared plus y plus s over 2 squared. So if we went ahead and plugged those in, we would get V equals kq over this value. So we plug in r1, so x squared plus y minus s divided by 2 squared. Close the bracket on that, and then subtract kq over the r2 value that we came to. So that is y plus s divided by 2 squared. Okay, so we're going to go from here and expand it out. So multiply the expand the square here. So v then equals kq over root x squared plus y squared minus ys plus s squared over 4. And then we're going to do this for the second part. So we have kq over the square root of x squared plus y squared plus ys plus s squared over 4. So we have this now, so we're going to use this. I'm going to go ahead and erase because I'm running out of space here. So we're going to go from here. And as we know from polar coordinates, r is equal to x plus y. So this x squared plus y squared is going to equal r squared. So if we plug that in, we have, I'll write it down here, v equals kq over root r squared now minus ys plus s squared over 4 minus kq over its similar value, which is root r squared plus ys plus s squared over 4. Go ahead and erase that now. So now we're going to divide this function underneath the radical by r, or by r squared actually. So v equals kq over root r squared times 1 minus ys over r squared plus s squared over 4r squared. And the reason why I'm doing this is because the equation we're trying to bring down to just r and theta values, and with the y hanging around, we can't really do that. So we use the function, or more like the rule, that says that any function that is like this, where x is so small that p wouldn't make a difference, which in this case the r value and the s value correlate to the x and p, then that basically equals 1 plus x times p. So what we're doing here is getting it into this form that we see here. So we have r squared times 1 plus ys divided by r squared plus s squared over 4r squared. So what we can take from this right now is, since r is much, much greater than s, these values of s squared over 4r squared go to 0 due to the fact that s is so minuscule and r is so great. So now we just have kq divided by the root r squared times 1 minus ys divided by r squared. And we can go further than that now to simplify, take out the r squared from the radical, and then form new equations that we can use this to solve. So now we have v equals kq over r, so that's how we took out the r squared from the radical, times 1 minus ys over r squared to the negative 1/2 minus kq over r times 1 plus ys over r squared to the negative 1/2 power. So now we're going to go ahead and rationalize this using this term that we have that I previously mentioned. So now we have v equals kq over r equals 1 plus ys over 2r squared minus kq over r times 1 minus ys over r squared. So now that we have this, we're going to go ahead and put the function all back together in terms of the kq and r's, and the ys is going to be converted into something more manageable for this situation with the radial terms. So now we're going to go from here and expand this once again. So we're going to have v equals kq over r plus kq ys over 2r cubed minus kq over r plus kq ys over r cubed. So as you can see, the kq over r's cancel, and now we're left with kq ys over 2r cubed, and two of them. Oh, forgot that 2 on that. And now we're going to go ahead and combine them. So v equals 2kqs over 2r cubed. Oops. 2r cubed. So as you see, the 2's cancel, and then we get v equals kqs over r cubed. And as of right now, it is not in the form that we're looking for with this 1 over 4 pi epsilon naught p cosine theta r squared. But we do realize that this now is going to become, to go into this form, we need to take the, whoops, forgot the y in there too. So we're going to take this and change it into this form. So a moment is classified as a force times a distance, and in this case the force is the charge times a distance. So we can actually pull out the q and s, because that's the distance between the poles times the charge. So that will equal p. And in this case, y, as you can tell from the geometry, y equals r cosine theta. So then we can go ahead and plug this back in now. So v equals kp r cosine theta over r cubed. So we get the r canceling and make this to r squared. So now it equals kp cosine theta over r squared, which now, I'm going to go ahead and bring this up here for a final answer. K we know is 1 over 4 pi epsilon naught times p cosine theta over r squared. And that is the same value that we see right here. That was the goal for the problem, and that is all.